Yeah, Ajay, we are all set to move
So,
ahead.
okay, fine, good. So, okay, so this second talk is basically focusing on the testing of the materials. Okay, and so I'm going to uh, focus more on the mechanical testing, and then first I will give you the brief overview of the materials aspect, material science, the basics of material science, where you will be able to relate if you are doing some testing on the material, uh, if material is behaving in a particular form, why it is behaving in that way, that you need to understand. So we will start with some basics, and then I will slowly go to the mechanical testing and explain you the each testing method and the procedure. And in between, you have any question, please feel free to raise your hand or ask question. Okay. So what I will do is now it is 8:18. So I will take around maybe half an hour, and then I will stop and take break for 5 minutes, and then ask you the doubts. Okay. Then this is how we will do the interaction. Okay. So I want to first give you the brief overview of the what you call is the you will be knowing about the different type of defects. Okay, so first you are aware of the different type of material categories. Okay, for example, metallic materials, and then we have non-metallic materials. In metallic materials we have ferrous and non-ferrous materials. Then we have non-metallic materials, we have ceramics, we have polymers, right? And so we have different categories of materials. I'm assuming that you are aware of those materials. And then if you go to the material science of these materials, all these materials, for example, metallic materials, they are having the a particular crystal structure. And when you say the crystal structure, like a arrangement of periodic arrangement of the atoms, in a particular pattern, right? And then you also will be aware about the different type of what you call defects. Okay, so I will just quickly go through the different type of defects, so that now you will be able to relate these defects and their role of defects uh, on the mechanical behavior of the materials. Okay, so when you have the different type of defects, we also say the imperfections. So there are four type of imperfections or defects. You can say one is the point defects and line defects, second one, and then we have the interfacial defects, and then bulk defects. So that is how we categorize them into zero dimensional, then one dimensional, two dimensional, and then three dimensional. So these are the different defects, and then you should be able to relate these defects where these defects are being used. Okay, so when we say the diffusion or semi superconduction, right? So these point defects are used there. Then we comes to the line defect dislocations. Okay, so when you try to understand the deformation or the elongation of the material, right? You try to understand through this line defect and the dislocation movement, right? And then this is how we represent the ductility, the area reduction, right? And then interfacial defect, we have the antiface, we have the grain boundaries, right? And then bulk defects, we have different type of cracks, voids, inclusions. So if you check on the on the particular scale, dimensional scale of these defects, then we have the electronic and point defects, that is of 10 to the power minus 12 centimeter we are talking about. Then we have atomic point defects of 10 to the power minus 8 centimeter scale. Then we have line defect, which you say the dislocations, they vary from 10 to the power minus 9 to 10 to the power minus something minus 3. Okay, then we have bulk defects, which goes from 10 to the minus 2 to 10 power 2. So it is on the dimensional scale, you should be aware what is happening. Okay, so the point defect, you will be knowing that we have the vacancies and then we have these self interstitials, right? So and then there are how to represent the vacancy, how to represent the self interstitial, that is one thing. And then we also have the equilibrium concentration of these point defects. Okay, so I'm not going in detail, but I'm giving you the brief overview. um, okay, so that now we will save the timing. Then we have the different type of defects in alloys. So if you have a different type of alloys like aluminum alloys, magnesium alloys, copper alloys, right? Then what you have the concept of the solid solution. Okay, so in alloys you have different elements mixing together. So you need to see how this solid solution, one element is soluble in other, at what extent, right? So this is how you understand through this solid solution concept. Okay, and then you will be aware about the Hume 3 principles, right? So Hume 3 principles, there are four different rules when you make the new alloys or new materials compositions. You should be aware about this rule, Hume 3 rules, where the atomic radius should be less than 15% of similar electronegativities of same crystal structure and valency. So these four rules you should be aware. And then we have also defects in ceramics. So you will be aware about the Schottky and Frankel defects. So I will skip this. And then when it comes to the line defects, okay, so these line defects plays very important role in understanding the mechanical behavior of the material. When you do the mechanical testing on any metallic material, you have to understand the line defect, you have to understand dislocations. So dislocations are basically line defect. And then you also need to understand it is a slip between the crystal plane when dislocation moves. So if I ask someone what is the definition of the plastic deformation, anyone can give the definition of the plastic deformation? Anyone? If anyone can give the definition of the plastic deformation. There are two definitions of the plastic deformation. One definition, you say that if you apply the load on the material like you do in the universal tensile machine, testing machine, you apply the load on the material, right? Then it it goes to the elastic, it has elastic deformation, as well as this has the, after the yield point it has the plastic deformation, right? So when you release the load within the elastic limit, material will come back to its position. You say elastic deformation. If it doesn't come, then you say it is the plastic deformation, right? But the plastic deformation means when the dislocation starts moving. If dislocations are not moving, there won't be any plastic deformation. So you need to have the line defects, so that no, you will have the plastic deformation in the material. Okay, hope you have got the answer and the concept. Now, how these line defects, okay, now line defects, I mentioned the dislocations. Okay, and dislocations are two types, you will be aware, like edge dislocation and screw dislocations. And then you have to apply the force and then dislocation moves, right? uh, and then you have the dislocation planes and then dislocations directions. Okay, so you have the two type of dislocations. Dislocation line, you need to understand, you can differentiate between the edge and screw. But most of the time we have the mixed type of dislocations where you have the edge and screw together. Okay, this is what is happens in the dislocations. Okay, so I'm not going through in detail, just to save the time I'm giving you the overview, so that now you will be able to relate what is happening. So this is the mixed type of dislocations where you have the edge and screw dislocations together. Okay, so this is looking like this. So then you have the dislocation loop as well. Okay, so this is the concept of so dislocation motion has to happen. Okay, so dislocation moves along the slip plane and in the slip direction. Okay, so perpendicular dislocation line, this is why you differentiate between the edge and screw. And then you have the Berger vector. So Berger vector tells you the amount, how much displacement is there, okay, in a particular direction. So slip direction will be same as the Berger vector. So you have the edge dislocation here, and then you have the screw dislocation here. Okay. And then if you go to the transmission electron microscope, okay, and dislocations you cannot see in optical microscope, you cannot see in the SEM microscope also, because of the what you call, you need the very high resolution microscope for that. So that is why transmission electron microscope is there. uh, and then you have to prepare these samples well. So the preparation for the transmission electron microscopes testing, you need to have the around 3 micron micron sample thickness. Okay. And then what you call is, you have to put into the grid where in the transmission microscope. Then why it is transmission? Because the electron will pass through the sample. Okay, sample is very very thin. Okay. And then you can only see the dislocations in the transmission electron microscope. So when basically these are the line defects which you are seeing in the transmission electron microscope, okay, micrographs, you can say. And then here they are the slip systems. So anybody knows about the close packing and non-close packing? What do you mean by close packing and non-close packing? So you will be knowing about the what do you call, the different type of crystal structures like FCC, BCC, because each material has particular crystal structures, right? Accordingly, it will behave. So FCC materials, if you say, there is a concept called is known as the slip systems, where we have the slip directions and slip planes. And in the close packing system, close packing plane only, the deformation will happen very easily. If it is non-close packing, so this is the example of close packing, this is non-close packing. Okay. And now slip plane and slip directions, I hope you will be aware. So total slip systems in FCC is like, there are total 12 number of systems in FCC, and then BCC we have 48. Now come to the tensile testing. Okay. So how will you understand when you do the mechanical testing on a metallic material, right? So if you do tensile testing on the aluminum sample, let us say aluminum is having the FCC crystal structure, and then on magnesium, which is having the HCP crystal structure. Now, when you do that mechanical testing on these two samples, right? So you have to basically prepare the sample. This is the dog bone specimen. Then you have the gauge length, right? And in between the gauge length, this will go to the grip of the machine, right? We have top and bottom overheads. Then you apply the tensile load. We have the load cell. Okay. Now what you need to understand is, you can see the two pictures here, but the behavior, the deformation behavior is different. It is looking like a very cone type of shape, and it is looking like a, this is not, this is looking like a very you can say it is deformation, but it is not that much having deformation but compared to the aluminum. So the difference between these two is very simple to understand. Is, you need to understand the crystal structure, you need to understand the slip systems. So, and closed packing planes. So basically aluminum is having the closed packing planes and directions, and that is why it is easy to deform, and it can deform significantly. Okay. And it is measurable as well. But in HCP, where our magnesium is having the SCP crystal structure, SCP crystal structure is having only one plane and three directions. So then that is why the deformation is very less. Okay. uh, so that is how you have to differentiate between these two different materials of two different crystal structures. So now you can calculate these things. You must have done this exercise in your. Now another thing is, when you do the deformation, the slip plane, right? The slip plane and slip directions, then you have these slip systems, right? So there is a critical resolved shear stress, right? And the critical resolved shear stress is represented by the is this is a famous law, Schmidt's law. Okay. And then when you have this dislocation, uh, stresses also will be there around dislocations, that also you have to differentiate. So where the compression stresses on the, so this is dislocation line, top part is having the compression, and then bottom part is the tension. Okay. And then once you have the dislocations, then dislocation also interact. Okay. So dislocation interaction will take place during the deformation process. And then when dislocation interaction will take place, then there is a mechanism called as the work hardening or strain hardening. So there is a famous rule, the Frank Reed source, where you can see I have shown you the dislocation line dislocations in previous slide. Then there are multiple dislocations and multiple loop of these locations will form during deformations. So this is all related with the uh, behavior of the material. Okay. Now another concept is you need to understand is the grain boundaries. Okay. So I hope you understand the meaning of grain, you understand the meaning of grain boundaries, right? And then so there are two type of grain boundaries. One is high angle grain boundaries and the low angle grain boundaries. Okay. So this is how you represent the align. Basically, is the angle of misalignment you compare. Okay. So this is the small angle gain boundaries, and this is the high angle gain boundaries. And this is how you can see, you can represent these two grains. And then we have the um, another coincidence side lattice. So this is another concept, but it's not required at this moment. Then another thing is twin boundaries. You will knowing about the twin planes, and then we have the mirror image of that. Right. So you will see this is the TM picture where you can see a twin deformation. So you can see a lot of twinnings are formed in the material in deformation. Okay. So I'm showing you this so that you will be able to relate the microstructure, as well as you will be able to relate with the fundamentals. Okay. And then another concept which is we have is the recrystallization, grain growth, and then the recovery. So these things are also there. This also things recovery, recrystallization, and grain growth also happen. Okay. In the form in the deformation process. So now how to understand, how to relate this, why I am doing this, I'm explaining this to you, is you have the grain size, you have the properties, mechanical properties, right? And this is all related with the microstructural changes. Okay. So you have the recovery phase, you have the recrystallization phase, and then you have the large grains formation. So how the properties, strengths will vary with these microstructural changes, how hardness will vary, how ductility will vary, right? These all these things are important to understand at this level. Okay. And then we have different type of heat treatments. So this is another topic, I'm not going through that, but heat treatment also we do uh, for the material. Okay. Now now let us come to the testing. So now you have understood the very fundamentals to on a material scale, material level, what to on atomic scale, what to do, different defects and dislocations, defects, line defects, dislocation lines, interactions, crystal structures, right? And then how these dislocation loops are there, slip systems, all these things. Now you have a material. Okay, you have prepared a material for a particular application, a function. Now you need to test the material whether it will fulfill that function or not, right? So what you have to do is, one simple thing all mechanical engineers do is they do the stress strain test. Okay, mechanical testing. So you have the metallic sample. So I explained that you have to prepare the sample, a dog specimen, ASTM standard sample. Okay. And then you have the gauge length. Okay. Like these 2 points you can see, you can mark these 2 points of gauge length. And these two parts will go to the inside the machine where you have two grapes, bottom and top, right? And now you will fix, and then you will apply the tensile load on this sample. Okay. So this is schematic. of loading as well as elongation is happening. Now, when you have the load and then you have the displacement or extension on the x-axis. Okay. Now, when you apply the load on the material, it will deform, right? And then it will go to the a point where if you release the load, it will come back to its position, elastic limit. And if you, after that, if you go beyond that, then there will be a yield point. So yield point is the point where you have the 0.2% strain, or you can say where you have the dislocation movement starts, okay, from that yield point. After yield point, if you release the load, right, it will have the plastic deformation as well. So when you calculate the total deformation, you will calculate like total elastic and total plastic. Elastic and plastic will become the total deformation in the sample. Okay, so you will see, you will also see that there is a significant deformation in the sample. Okay, so you have the proportional limit, you have the elastic limit, yield point, necking point, and fracture point. So basically, this picture will show you the this is the behavior of the brittle material. This is the behavior of the ductile material and some other organic material. This is the typical behavior. It is not the exact any material, but typically ductile material behaves like this. Brittle material behaves like this. So they have the deformation, and then at the point they will, with minimum deformation or negligible deformation, they will fail. But in ductile material, they will have significant deformation. Okay, and then after that they will have the failure. Okay, clear? So this is the thing. So this is the different pictures for the different materials, like low carbon steel, then you have the low alloy steel, low alloy steel. Now one point, if I can ask you, um, that in a mild steel material, you can see there is a lower yield point and upper yield point. So only mild steel shows that type of behavior. Okay, so basically there, and the concept is the happening is the, I mentioned the dislocations are there, and then they are the alloying elements. So dislocations are interacting with the alloying elements, so the behavior also will change that time. So that is how you see in that, in the testing, during the testing. Okay, so this is the thing. Now let us go to the more detailing in the testing. So when you do the mechanical testing, let us say the you have the metallic sample, and then there are two things you need to understand. Is one is the, you have to calculate the engineering stress strain and true stress strain. Now I would like to ask a question. Anyone can answer. We have the Hooke's law, right? So that, what is the Hooke's law? Can anybody say the Hooke's law? And that Hooke's law, can we apply after the yield point? Let us say in this region, can we apply the Hooke's law? Or let us say in this picture, okay, here. So we have the Hooke's law that is valid within the elastic limit. Okay, we cannot apply the Hooke's law in the plastic zone, okay, or during plastic formation. So we have the different law. We say the Hallman or power law equation, where the plastic, the strain hardening component is added, strain hardening exponent is added there. So in this plastic deformation, we we represent through the power law equation, and here we have the Hooke's law. Okay, so Hooke's law explains within the elastic limit, after the yield point, the what do you call it, the Hallman equation, and then you have the engineering stress, engineering strain, true stress, true strain. I hope that you are aware of these true stress, true strain. So in true stress, true strain, we are only using the instantaneous cross sectional area. Okay, so but if you see the engineering stress and true stress will be more than engineering stress, because if you see the stress uh, formula, you have the load divided by area. So if area is reducing with with your, when you are applying the load, area reducing stress should increase, right? When you are using the instantaneous cross section area, but in case of the engineering stress, you are using only original cross section area. So that is why the true stress is more than the engineering stress. Okay. So this is how the difference between the true stress and engineering stress, and then there is a relationship between the true stress and engineering stress, and that also you should know, because this is what you are going to use and you are going to explain uh, in the mechanical testing of the material. Okay, so when you are, because this entire thing you have to do the calculation. So when you are doing mechanical testing and you are asked to calculate the strain hardening behavior of the material, then you need to use this concept is true stress and true strain and the Hallman equation. Okay, so this is how we do the calculation. You must be knowing this. So this is the power law equation. Okay, you cannot use the Hooke's law in the plastic deformation zone. Okay, so that is why the Hallman equation is also known as the Hallman equation. So you need to basically explain the strain hardening behavior using this strengthening coefficient and strain hardening exponent. Okay, and here basically the dislocations are playing very important role. Okay, because strain hardening is happening because of the dislocation interactions. So when dislocations are interacting, entanglement will happen. Okay, even dislocations loops also we will observe, right? And because of that the material is being hardened. So you can see here, you can see the stress will increase. Okay, and then once it goes to the UTS point, at UTS point you will see the point ultimate tensile strength. After that the materials instability starts. Okay, so materials instability means the necking will starts, and then also instability means the cracks starts forming in the material. Okay, a lot of small voids will form at the instability point, and then after those voids will college together, and then further they will grow, and then finally you will see the fracture of the material. And ductile materials will have the uh, cup and cone fracture, we say, and then brittle material is having very minimum fractures. Okay, that we say. So this is how you do the calculation of the true stress, true strain, engineering stress, engineering strain. Hallman equation, you have to calculate the K value and N value. How to calculate the K and N value? This is very important, because when you interpret your data of your material, when you are developing a new material or new alloy, right? You need to also understand the plastic behavior of the material. And the plastic behavior you can only understand by using this exercise which I am showing here. So basically you have to apply the Hallman equation, you have to calculate the strengthening coefficient, you have to calculate the strain hardening exponent of the material. So this is how you can calculate the strengthening coefficient and strain hardening exponent. Okay, and then the plastic instability. So when you have the plastic instability where the df is equal to 0, it means that the uh, the the uh, the maximum load, okay, where decrease the cross section area. Okay, and then from here the material will basically uh, uh, starts yielding, and then cracks will start forming in the material. Okay, so this is how you have to do that. Okay, now, so this is what I have explained you how to do the mechanical properties. And then first you prepare these samples, and then um, applying the um, tensile load, and the same thing applies to the compression load. The behavior will be different. And basically in tensile mode you are opening the crack in the material, in the compression you are closing the crack in the material. So you have to see your material is used, is applicable for the tensile load condition, or is made for the compressive load applications. Accordingly you have to see, based on the testing of the material you can find out. Okay, so this is what I have clearly explained you. This is better explanation. So I hope that this will give you the clear picture to you. And yield point, and then this is the plastic region here, this is the elastic region, and this is the fracture point. Okay, so from here you can calculate the Young's modulus. Okay, and then Hooke's law is valid in the elastic region. So you have to understand the definition of elastic deformation I have explained, and plastic deformation, and then ideal plasticity and non-ideal plasticity. So in non-ideal plasticity, I have explained about the strain hardening, where dislocation motion is there, dislocation multiplication and entanglement also is there. So I have shown you the dislocation multiplication mechanism where the lot of dislocation loops will form. Okay. So this is how you can calculate the yield strength where 0.2%. So many of you will be aware that when you do the testing, nowadays the automatic machine can give you the data. Okay. Uh, but you also should know, verify manually. The machine is sometimes there will be some error. So you can also verify using the manual calculation. You calculate the yield strength. Yield strength is the point where dislocation starts moving, or you can have the 0.2% offset, okay, on the strain, and or you have the 0.002 strain, that is called the yield strength. And then I mentioned that yield point, upper yield point, lower yield point, it is basically the interaction of dislocations and the alloying elements. And this only you can only see this behavior in the ferrous alloys. And uh, and and then I've explained you the relationship for the yield, for the engineering stress and true stress, and necking. Okay, you also need to understand necking. Okay, so necking, I mentioned that the mechanical materials instability starts from the UTS point. And so if you compare the true stress versus engineering stress, I told that true stress will be more than the engineering stress. Okay, this is how you calculate the engineering stress and compare with the true stress. Okay, they are all the basic relationships, okay, and equations. I think you must have, most of you are teaching this, and some of you are students, and most of you will be using these equations and doing the test. Okay, and using these things, relationships, so elastic and plastic. So now this is very important here. When you are doing the mechanical testing for the metallic materials, you should know the elastic deformation, you should know the plastic deformation. Okay, so sigma elastic and sigma plastic. Okay, and then the total entire deformation you have to calculate, so to understand the total deformation in the material. Okay, elastic strain is recoverable, but plastic strain is permanent. That is what you have to understand. Okay, so yeah, so this is what I have explained to you. Something is missing here. Okay, yeah. So this is about the mechanical properties, and another thing is the elastic modulus. Okay, before I go to the elastic modulus, yeah, let us first go to the elastic modulus and understand elastic modulus. Can anybody elastic modulus is the material property. Okay, um, and it plays very important role in designing the material as well. Okay, so elastic modulus is the material property. So can anybody tell, if I want to uh, increase or decrease the elastic modulus, um, how we can do? Suppose we need a material of higher elastic modulus. Is it possible? Is it possible to modify? Is it possible to modify, change the elastic modulus of the material? Anyone? Anyone? Elastic modulus is material property, and basically elastic modulus is linked with the bonding in the material. So you must be knowing about different type of bondings. We have primary bonding and secondary bondings. So bonding, if you can alter the bonding in the material, okay, you can alter the elastic model of the material. Okay, so So that is what you have to understand. Okay, now let me give you the different type of strengthening mechanisms. So I have explained the mechanical testing of the material. I have also explained the different type of properties calculation in the material. Then I have explained the Hooke's law and the Hallman equations, and which one you have to use for the to represent the to explain the elastic deformation and also the plate deformation. Now you also need to understand the strengthening mechanisms. Okay, so strengthening mechanisms are five. One is the strength hardening, then we have gain boundary strengthening, then we have the solid solution strengthening, dispersion strengthening, and precipitation strengthening. This is how we understand this different type of strengthening mechanisms. Okay, and we represent in this form. Okay, so without going in detail because the time is limited, so I will tell you the what is the importance of these strengthening mechanisms. Okay, strengthening mechanisms will tell you or explain you the strengthening behavior in the material, and which strengthening mechanism is contributing in the strengthening the material. That is how you can identify, and that is how there one is the strength hardening and yielding, where I mentioned that when you have the strength hardening in the material, you will have the what you call dislocation entanglement. Okay, when a lot of dislocations will move together, they will entangle, right? And then you have to apply more force to for the deformation. That is how the strength hardening taking place. Okay, and then there are calculations for that. Okay, so you can calculate the shear stress in the material, and you can also calculate the distribution density in the material, and then depending on that you can calculate the contribution of the strength hardening. Okay, in the material. Now another uh, strengthening mechanism is the solid solution strengthening. Okay, so as I mentioned that when you have the alloy, uh, there will be a there will be secondary element materials in the alloy, right? Alloying elements you can say. So what happens is these alloy elements, they also form the uh, precipitates, right? So when you have the dislocations and then these precipitates, right, so they also interact each other, and sometimes they also hinder the deformation, right? So this is how the solid solution strengthening takes place in the material, and that also plays an important role. And another thing is the dispersion strengthening. So this is the example where you have the dislocations, right? And then you have the different dispersed particles, or you can say the secondary particles in the material, right? So what will happen is dislocations can form the loop along or surrounding particles. So they are forming the loops, they will form multiple loops, right? And then this is how the dispersion strengthening will take place. Okay, and then we have the precipitation strengthening. So this happens generally. That's why we do the what we call the heat treatment for getting these strengthening mechanisms. Okay, and so basically, just to without going in detail in this because it will take time. So what you need to understand is you need to understand the five different mechanisms um, in the material: strength hardening, gate boundary. So gain boundary strengthening, we you will be knowing about the Hall patch equations. If you have the smaller grains, they will give you the better properties compared to the large size grains. Okay, so this is how you can understand the strengthening mechanism. So five strengthening mechanisms, and then the mechanical testing. Okay, and then calculate all the mechanical properties of the materials, and then this is how I have explained you, right? So now I will stop here. Okay, because and then I will open for the question answer if anything is there. Yeah. So some of you may be the research scholars, or some of you will be the faculties in the colleges. So you will be teaching also these courses. So, but if you have any doubt or if you need any clarification, you are feel free to ask.
We have removed the restrictions of mute. Participants can ask any questions.
Yeah, Ganesh Chate want to ask something. He unmuted.
No,
I see 100 participants in this, Dr. Binayak.
yeah.
Yeah, so yeah, they can raise their hand and they can ask questions about the mechanical testing of the material, any doubt they have, or clarification they ask.
I had a few questions.
Hmm.
Yeah, I was waiting for others to ask first. So, okay, let me ask you questions.
Yeah.
Uh, yeah. The first thing is about characterization of functionally graded materials.
Hmm.
Uh, any thing that you want to suggest to the audience? Like, uh,
So now here I have covered most of the. You are saying functionally great materials, right?
yes, yes, yes. So, which
Yes.
of these can be used?
Yes. Yes. So basically, functionally great materials are the materials where we are also developing some of these materials. So you will have the layer of materials, and where each layer of material will have a different property, right? And then along the gradients of the material which you develop, along the gradients or thickness or cross section, you can measure the properties. Now which property you want to measure? First is mechanical properties, second is the microstructural properties. So let us say mechanical properties. You can, you first, the important property in the functionally graded material says the interfacial strength. Interfacial strength, you can calculate, you can do the measurement in the mechanical testing. Basically you can do the shear testing, uh, shear testing, okay, just to check the interfacial strength. You can also do the testing in the tensile mode to check the bonding at the interface. And before you go to the mechanical testing, you should also do the microstructural testing at the interface and check whether the interface is defect free. If any defect is there, then there is no point of going directly to the mechanical testing. So first I will suggest here that first you should go for the microstructural testing. Check the interface, whatever gradient you have generated or created in the material, that wherever there is a abrupt change or there is interfacial change, there you should check the microstructure and make sure that that is defect free, and then you go to the mechanical testing. Then you can get the better result. So you can do the microstructural testing first at the interface. You can use the optical microscope uh, at the first step, and then if you further want to go to the higher magnification, understand the grains and other things, then you can check. You can use the SEM, scan electron microscope, and then if you want to check the dislocations at the interface and other things, then you can go to the transmission microscope. So it all depends which facility you are having, and then after that you can do the mechanical testing. So mechanical testing you can do in shear mode as well as in the tensile mode. So shear mode is preferable so that we can see how the interface are intact.
Yeah. Any suggestions? If the sample is very small and we want to do that
So,
shear
so
thing,
sample. So here the thing is, if your sample is like a micro samples, right? Uh, so you have to see. It all depends which process you are using for making the samples. For example, if you are using the manufacturing process where you can easily make a bulk sample of a little larger size, then that is better. uh, and if you don't have that facility to make a bulk some bigger samples, then some people, for example, I will give you example. Some people are using the powder metallurgy route, okay, for making the compact, okay, of different metallic layers they will do, and they will make a compact, they will make a cylindrical specimen, okay. So cylindrical specimen for micron samples, at least you need a significant uh, thickness and the length. So then that time what you can do is, you can do the micros, you can make the micro samples, okay. There is a standard for, but ASTM standard, but ASTM standard sometimes we don't follow for the micro tensile testing, okay. We do the customization, but there are some standards we follow, you make for the micro tensile testing, okay. And but I will suggest that if you are able to make a sample uh, of a large length, large dimensions, that will give you the better result, okay. And also acceptable for the application, okay. Because these functionally graded materials, when you are having at least 3 to 4 layers, right, you should have significant uh, uh, dimensions of the sample to understand the entire behavior. Otherwise, if you make the micro sample, it may not cover the entire cross section of the sample. Getting my point?
Yeah. Yeah. Before
Yeah.
I move to the next question,
Uh,
anyone has raised the hand, they can ask the question.
I
Anyone,
see. I see. Some people were raising the hand.
they can unmute themselves and ask, because we have removed that mute
I,
restriction.
I see Yogita Poddar was raising the hand or unmuting things.
Okay. If they are a little apprehensive to speak, they can type their queries in the
Yeah.
chat box.
If you cannot speak, then you can write in the question. This is a chat box, right? You can use chat box. But
Okay.
these are the common testings, okay. Functionally graded materials are now having a lot of applications, okay, as well as even in the what you call, um,
There is
even
one,
additive manufacturing process also being used to make the FGM materials. Somebody have some question?
yeah, yeah.
Chat box.
Box, yeah.
Mike,
Uh,
where micro tensile testing facility is available in India? Micro tensile testing facility is available in most of the institutions. Okay, the institutions, like where they have the sophisticated UTM machines. Okay, the only thing is use the you have to make the dies to hold the micro samples, okay. That is the only thing I think you may need. Otherwise you can use your UTM machine available in your college or in your institution, okay. So most of the institutions are having the facility. We have it in VTU Belgavi. Yes, yes, correct. So the powder context, what is that powder contact?
or powder compacts. Powder compacts.
Especially for powder contacts, powder compact.
Yeah, means
What is
powder,
compact?
they make powder compacts and sinter it,
Yeah.
small pellets.
It all depends on your die size. Okay. If you are able to make the compacts, because dies are costly affair. Okay, you have to make dies of to make bigger samples. If you are able to do that, then you can do for powder compacts as well.
Okay.
Yes.
Now, taking it to the next part, now many of them are inquisitive about knowing where all such facilities or colleges, people or researchers who belong to tier 2 and tier 3 kind of a city or a place
Yeah.
or private colleges, any ways, any channels, any platform where they can get their test done. Where just like STEM is there,
So
iSTEM is there.
actually now government of India has one portal. They have ISTM portal. You will be knowing that. So ISTM portal, like all IITs, NITs, or R&D labs, they have the equipments in their place. They have uh, put their list of equipments. Okay, so if anybody wants to use any equipment, they can go to the ISTM portal, and then they can find a nearby institution where that particular facility is available. They can directly book the slot there, and once they get the slot, they can directly go to the institute. That is one approach. Second approach is, if any institution which is near to your place or college, for example IIT or NIT or any R&D lab, you can directly approach them or write email to the facility in charge, and then they should be able to, I think, encourage you to do the testing in their place. So at, for example, at IIT Tirupati, we are using both mechanisms. Okay, so people are coming through ISTM portal, whoever needs facility. People are coming through by they direct like they write email to us or department that they want to do the testing, and then we accordingly we allow them to come and do the testing.
Yeah. There is one question from the room here, coordinating group. This is with respect to your metal air batteries, which is we wanted to ask that time, but since there was a quick break, metal air batteries.
Ha 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 ha.
Yeah, can you just shed some light on it? And can you just tell like how is the progress in aluminum air batteries?
Aluminium.
Aluminum air batteries.
Ha ha ha. Okay, okay. So I am not aware much about the aluminum air batteries, the progress. The thing is now, you will be, most of you will be aware that the lithium ion batteries now are still not established. Okay. Now when you talk about the aluminum air batteries, they are not into even the development mode. So if you take the example of India, we have only one or two plants now. Amara battery, they have opened the lithium ion battery plant in Telangana, and still they are working on it. Okay, so uh, I am not aware much in the what is the progress going on in aluminum air batteries, but I can say that there is not much progress, because we are still in the phase of uh, producing lithium ion batteries. Okay, and then until we come to a established mode, uh, yeah, research is going on. A few people will be doing research, but when it comes to the production and uses in the different applications, it is not there much. Yeah, that is what I can say.
Now, since you are still in the establishment mode of lithium ion batteries,
So sodium ion batteries. So the sodium ion batteries now, people are talking about the what do you call now if you take the example of the China is developing these sodium ion batteries, and they have entered into the even development mode, right? But if you say the India even now, only Amara battery is developing the products in their plant, but sodium ion battery is also not there now in the development mode. Okay.
now one very like specific from commercial point of view, this question is with respect to your lithium ion batteries. Now the raw material, that's a lithium and
Ah,
electrolyte. Uh,
yeah.
so like, is
So,
it
the raw material is the challenging thing, okay? Because everything, these things depend on the raw materials, okay? So India is lagging of these raw materials availability. So that is where they are importing the materials, and the cost also is increasing, okay? So what is happening now? So they are also looking for the alternative solutions. Can we develop alternative materials? Today we are talking about lithium, sodium. Tomorrow people will come up with some other material. Okay. So still the work is going on. So because the country, because it will depend, no, country will be dependent on other countries to get the raw material. Suppose another country doesn't supply the raw material, then you are locked, right? You are locked. So so raw material availability plays very important role, and that is why only few industries, for example, I am saying that Amraza battery, they are the largest, they are the second largest player, battery player in the country. Okay, so they are able to do that because they have that capacity to, even in Tirupati also they have they have plants, right? So they are doing that, they are doing that. But raw material availability is challenging for us. Even now people are talking about the rare earth materials. Even now other countries are focusing on the rare earth materials. We don't have those materials availability in the country. So we have to focus on the material which is available with us, right? And then develop.
Yeah, this is very important because,
Hmm.
like in a population like India, where
Yes,
140 crore
yes,
plus,
yes, yes, yes.
majority of them are using mobile phones.
That's what I'm saying. That is
Whatever
what I'm
lithium
saying.
is
That is what I'm
being
saying. That is what I'm saying. So government is now also working on mining of, looking for these resources whether they are available in India. So they are looking for the locations, they are looking for their minings where mining can be done, right? So the work is going on. The government is aware of this. That is why a lot of missions are going on, like semiconductor mission, and then this hydrogen mission. A lot of missions. This is their mission projects of government, right? So whether, see, some of the things will not come into the public until it is established, right? Right, because they also have to, government will not reveal many things in the public, but we are not aware. It may be there, it will be going on in the back end, right? So but time to time it comes in the public.
uh, like just like means in nuclear kind of fuels, uranium was not available in India. That's why thorium has been explored.
Yeah,
Uh, so just like we can make a statement
same thing
right now.
same thing for nuclear materials similarly. So the thing is that the research will keep going. Okay, but the resources, the raw material availability is required. Okay.
So lithium, as of now, there are no sources within India,
Yeah,
naturally.
yeah.
So we are importing it from outside.
But how long will you import? That is the question,
Yeah.
right?
And
How long?
major source is China, I think. It's through
Huh, huh.
China only we are getting it,
Yeah,
right?
yeah, yeah,
Any geopolitical situations are uh, abruptly
yeah,
created and
yeah. Because these geopolitical situations plays very important role when it comes to these things, and they are crucial materials, right? These materials are very crucial, right? Even the semiconductor industries, if you see, right? So these materials are very crucial. Even in COVID time, you must have seen, right? Right, you must have seen the situation when we were not having the supply of materials, right? Because of that, we everyone faced the challenge.
so that's one weakness with us that
Yeah,
lithium is not available in India.
yeah,
We are importing it. Anybody stops supplying us, then we'll be in big trouble.
yes, yes,
The majority of the electronic gadgets, right from mobile phone,
yes.
which more than wife, we spend
Yeah.
time with the mobile
now
phone.
now government is taking initiative, and they are now bringing the industries in India. They are trying to manufacture in India, assembly in India, right? All these things, but right now we don't have that, right?
Laptops, yeah, mobile phones.
Every second item is coming from China, especially electronic, with electronic item, right? So because they are able to do it.
Why this point was raised? Because participants can think in this direction, and that was one of the objectives of FDP,
Yes,
that
yes,
more human resources brought in this direction, so that more and more faculties can take this as their research and work in this
yeah, yeah.
direction.
Lot of now research is coming up in the direction, and government is having a lot of now schemes also. Faculties can apply to those schemes, and if they have some innovative idea, they can apply for funding and start doing some research, right? And also a startup. right? A lot of startups are now coming up. If any faculty or student is interested in this thing, they can definitely do that.
There are a few questions in the chat box. Should we read it or can you see it, Ajay?
What is that? The definite solution for welding 3D printed parts. Is there a definite solution for welding 3D printed part? Okay, so you want to weld 3D printed parts. Yeah, 3D printed part you want to weld, right? So you can weld 3D printed part if it is, yeah, it is possible to, but definite, the solution depends on the basically what type of part it is. Okay, it depends on that. uh, you can have different type of welding process are available. Okay, so even the conventional welding and also other welding processes are now coming up. You can use those welding process for, so basically you want to weld the 3D printed parts. Yes, it is possible.
Yeah, and then Anil Polji is asking about difference between sodium ion battery and lithium ion battery. And the same he has continued like what can we reduction of the size of the batteries. And is there any like in India related to this testing? Yeah, battery testing facility he is asking.
So battery testing facility is available. I mentioned that Amara Raja battery is having the battery testing facility. Okay, so I will suggest that if you are interested in this more, I can connect you uh, with them, and you can plan a visit to their battery plant. Okay, where you can clearly see even the manufacturing process of the battery also you can see in their plant. Okay, uh, so you can think of, I think, Dr. Binayak, you can,
Yeah,
if any candidate like faculties or students, if they are more interested to know uh, in this domain, then I can provide the connect, and then you can arrange a visit, or they can go from their college, no, in a group, and visit the battery plant. So when you visit the battery plant, you will be able to see the manufacturing process of the batteries. You will be able to see the testing bed, okay, and the entire thing. You will be able to see.
yeah,
Yeah,
that's very nice of you, sir.
yeah.
Uh, yeah, so any more
So
questions
another
on
question like joining of two similar material for making permanent assembly. Okay, he is answering. I think he is, instead of questioning, he is answering. Okay.
answer? Yeah, yeah.
Yeah. So I think if people have more questions, they can even send by email also, right?
So now I think we will float the feedback form in the chat box.
Yeah.
So people can start answering that attendance come feedback form. And if there are no more questions, we thank our today's speaker, Dr. Ajay Kumar ji, for an
Thank
excellent and intriguing session. So particularly the aluminum, somebody is, yeah, particularly the battery things where people can take up in their research work, who have completed PhD, they can float this problem for their prospective students as a PhD problem. And those who are doing PhDs, they can take because energy sector is one of the sectors which is more attractive and it can like easy to get funds if the proposals are on this energy related kind of thing. So that's about like what we wanted to say. So I thank once again Professor Ajay ji, Dr. Ajay Kumar ji for an excellent two sessions. Thanks a lot. Thank you, Ajay ji.
Yeah. Thank you. Thank you so much. Yeah. See you all. Take care.
Thank you, Ajay. So participants are requested to.
I am leaving now. I am leaving now.
Yes, Ajay ji. Yeah, yeah, you can. Thanks a lot. Thanks a lot for
Yeah.
sharing it.